Okay, so this is the first part of forces. This one we're interested in the resolution of forces, in other words, unbalanced, balanced forces, looking at F equals ma and deformation of solids. So first thing we look at is what can forces do? Essentially, the main thing that they can do is they can change the motion of an object. Okay, so what do we mean by that? We mean by acceleration, so either deceleration or acceleration, or it could also be changing the direction. Okay. The other thing that they can do, and that's showing up here at the top here, so you can push a ball, you can push it again to change its direction or stop it. You can push it to change its direction here, so hitting it at an angle will make it curve. And the last thing that you can do is all this stuff is change the shape of an object. Okay, so in other words, we could deform it. Okay, so the force extension experiment is one we're going to do in class. But essentially, we have a mass that we hang onto a spring, and that has a weight. And we add more mass, we get a new weight. Now that weight creates an extension. Now extension is equal to the change in length from the original length. Okay, so what you do is you grab your original length, let's call it x0, find your new length, L, and take it away, and then it gives you your extension. So in other words, if we add on 50 grams, that is 0.5 newtons, so 0.05 kgs times 10 for gravity. So remember, weight equals mass times gravity. And 100 grams is, let's say, 1 newton. And if we get a length at the start of 4 centimeters, and if we then find the extension for just the hanger, 0 centimeters. 4 minus 4 is 0. For this, let's say we had 6 centimeters for the 0.5s, that gives us an extension of 2 centimeters. 6 minus the original equals 2. Let's say we had 8 centimeters, that would be 4 centimeters. So extension is how far you go from the original length. So what we're going to do is we're going to graph it. When you graph it, you get this line here. Okay, nice straight line at an angle. Now, if you carry it on with a spring, it will curve. Okay, but we'll look at that later. So, what happens here, you can see what's sort of happening. You add a newton, you extend by 0.1. If you add another newton, you've extended by another 0.1. Another newton, another 0.1. Okay, what we're going to do is we're going to find the gradient of this force extension graph. So let's just rise over run. Change in y over change in x. So that is 4 minus 0 is the change all the way up to there. 0.4 minus 0. Okay, if we work that out, what's 4 divided by 0.4? Now what's the units? The rise is newtons divided by the run of meters, so in this case it's 10 newtons per meter. And that makes sense, so to extend this object by a meter, you need to apply 10 newtons. So what does all that mean? Well, it relates to this formula here. The equation of a straight line is y equals mx. Okay, in this case, our y values are f, and our x values are x, and so our gradient, we're going to give it a value k. So, if you graphed force versus extension, found the gradient, that's equal to k. So let's say in the last example the gradient was 10, so f equals 10x is the formula for that spring. So if I wanted to find the force to extend it by 3 meters, I'll have 10 times 3, which equals 30 newtons. So the last thing that the graph can say, once it actually starts curving, then we're no longer proportional. It's no longer a straight line. So limit of proportionality is where the graph starts to curve. Hooke's law tells us that force is proportional to extension provided the limit of proportionality has not been passed.